And the next speaker is Fathi Namouni from the Observatoire de Nice. We speak about the first research of Michel Hénon.
Est-ce que je vais utiliser juste directement I will start in French and then I'll move to English. Avec certains intervenants aujourd'hui, notamment Jérôme Pérez et André Sobolewski, j'appartiens à une génération de chercheurs qui ont connu les travaux de Michel Hénon à l'université. Donc, vous imaginez ma joie quand lors de ma soutenance de thèse, en 1995, j'ai rencontré pour la première fois Michel Hénon, qui était un des examinateurs de ma thèse. À cette époque, je ne savais pas en fait que j'allais avoir le privilège, 9 ans plus tard, d'être recruté par l'Observatoire de Nice et de partager le bureau de Michel Hénon. J'ai choisi ici aujourd'hui, afin de célébrer donc l'œuvre de Michel Hénon, un travail un peu particulier qui ne rentre pas à première vue dans les résultats que l'on considère comme étant les plus célèbres. Mais vous allez voir en réalité ce travail-là qui est la première publication de recherche de Michel Hénon en 1958. Vous allez voir que ce travail a eu des ramifications dans plein de domaines d'astrophysique et que dans la liste citée tout à l'heure par Uriel Frisch, la liste des grands savants dans lesquels on doit mettre Michel Hénon, il faut aussi rajouter Chandrasekhar. So, I'm going to talk about Michel's first research paper entitled in French Un calcul amélioré des perturbations des vitesses stellaires. In English, an improved calculation of the perturbation of stellar velocities. This was the first paper that Michel has published when he started working on globular clusters. And the object of this paper deals with the concept of dynamical friction. Dynamical friction is a macroscopic force that is present whenever a perturber moves in a physical medium, interacting with it only gravitationally. Then the perturber will raise a wake, a gravitational wake in the medium, and this wake will drag back the perturber. What you see in the pictures that I show is a particular situation of a perturber moving in a gaseous medium, as opposed to a collisionous medium like a globular cluster. For example, you have examples at low Mach numbers, subsonic, transonic, and supersonic. But dynamical friction was not discovered this way. It was originally discovered in the context of stellar dynamics, obviously, and the relaxation of star clusters, and we heard about those in an earlier talk about Jérôme Pérez. Dynamical friction was discovered by none other than Subramanian Chandrasekhar in 1942-1943 as a necessary macroscopic force in the following way. He reasoned that the theory of random flights or Brownian motion would lead in a collisionless system to the linear time increase of the velocity, the square velocity dispersion. However, in order to maintain a Maxwellian distribution function, that he would call that would describe what he calls a conservative system in this article. Friction needs to be present in the system to limit the increase of the velocity dispersion. He then described the distribution function of the system using a Fokker-Planck equation. And with the classical Fokker-Planck equation, we have friction and diffusion parameters. And he made the following assumption, that the diffusion and friction coefficients are evaluated from pairwise stellar encounters. You have seen before the movies that Jérôme Perras had shown, and it might be at first sight a bit surprising that a pairwise binary stellar encounter would describe such a system, but actually it's not a bad approximation. However, there was a small problem or snag. The snag is this. If you take a star and you try to calculate the deflections that other stars force it to have, and average over all stars, this average would be, for example, the impact parameter. This is the test star. The impact parameter of the perturbing star is this, what Chandrasekhar in his paper calls D. Then when you average over all values of D, and Chandrasekhar considered a homogeneous medium that is infinite, then you realize that basically integrating over the impact parameter, you will have a divergence because the gravitational potential goes like 1 over r, and therefore you will have a logarithmic divergence. So in his famous astrophysical journal paper, what Chandrasekhar did, he did the following thing. He devoted 3 lines, as you see, this is a copy of the paper, to the issue, saying that the integral over the impact parameter d, when extended from 0 to infinity, diverges, but for reasons explained in stellar dynamics, that's Principles of Stellar Dynamics, as we call it now, page 56, we allow for d only a finite range of integration, namely from 0 to d0, where d0 is of the order of the average distance between the stars. So as the upper cutoff, he has to account for all the stars that are in the medium. He would actually cut off the contribution of stars at length d0, where d0 is the inter-star distance. So this is a bit unusual, so we have to go to Principles of Stellar Dynamics to understand why he did that. And this is a copy of the relevant paragraph. The idea that there is a divergence, Chandrasekhar says, is due to the fact that we're considering binary encounters, therefore the 2 stars are coming from infinity. And well, that cannot be correct for various reasons, because among other things, a second star will be encountered before the first has finished its encounter. So he goes, if I can read, thus the divergence of the integral occurring in 213.8 as d tends to infinity must be attributed first to the general overestimation of the energy exchange delta E, which is of particular importance for the distance encounters, and second, to the increasing difficulty of describing stellar encounters on a 2-body idealization of the corresponding impact parameter. Idealization, actually, I can't see very well from here. Idealization when the corresponding impact parameter becomes of the same order as the average distance d0 between the stars. And so he goes later on saying that in a general way, it is clear that the cutoff dmax should be equal to d0 within a factor of 2 or 3. It would be difficult to estimate dmax more closely than this without going into considerable amount of detailed calculations. Then he goes, however, it is seen that an error of factor 2 or 3 in the chosen value of Dmax does not introduce any significant error in the final expression for the time of relaxation. This fortunate circumstance arises from the logarithmic divergence. If you have something, a log, something proportional to d0 inside the log, it doesn't matter because the log will be small. Well, that actually didn't satisfy everyone in the community back in those days, but one community solved the problem rather simply. Back in those days, two communities interested in n-body gravitational systems were astronomers and plasma physicists. And plasma physicists had a natural cutoff at longer distances, which is the Debye length, the screening length, that they could use safely to cut off this integral, which physically has meaning. However, in astrophysics, it was a little more complicated. That is when a young PhD student, Michel Hénon, enters the picture. And he offers us what he calls an improved calculation of the perturbation of stellar velocities. The idea when one reads Michel's paper is this, that he doesn't believe that this divergence comes from the three-body interaction, that the next star is going to be significant. He believes that the pairwise stellar encounters should represent the physics of the system. And therefore, he believes that the problem is related to the fact that we're integrating the effect of the binary encounter for an infinite time. And this will be one of the lessons that we learn from this paper, that whenever we use an infinite medium and steady state waiting for infinite time, we should be very cautious, because maybe sometimes when we have divergences, we can go back and remove these hypotheses and actually everything will be convergent. And that's what he does. He takes a star that travels at time t. That is not infinite, this is finite. And he goes, a star travels at time t, hyperbolic deflection is complete for stars that are very near the star, for small impact parameters. Whereas if the star is very far away, what it does, it perturbs just a little bit, but not too much, just a little bit, the test star. How does he do that in practice? He would apply complete hyperbolic encounters for nearby stars, and he characterizes them as those encounters where the impact parameter is much smaller than the travel distance. And he would have a slight deflection for faraway stars when impact parameters are much larger than the interaction distance being the mass divided by the velocity squared. In the second case, which was not treated by Chandrasekhar assumed that all stars were treated like the first complete hyperbolic encounter. He uses celestial mechanics perturbation theory to calculate the small deflection. In practice, however, the interaction distance is always smaller than the travel distance. And so this is what Michel does in his paper. He takes a distance L, that is between the interaction distance and the travel distance. He applies the full deflection for all parameters from 0 to L, from impact parameters from 0 to L. And then from L to infinity, he integrates over everything. He applies this light deflection that he obtains from classical celestial mechanics perturbation theory. So, what does he find in the end? Well, for the diffusion coefficients, he could determine something that was not determined before, which is the contribution to the velocity dispersion squared of the stars up to a distance, up to an impact parameter d from the test star. And he notes, for example, that the parallel velocity dispersion has contribution only from nearby and faraway stars. That's the curve A. He notes that for perpendicular velocity dispersion, there is an increase there is logarithmic increase until the distance becomes comparable to the impact parameter becomes comparable to the distance that the test star has traveled in the system. This is a main difference. For the friction, he found the following formula. And I have shown here the formula by Chandrasekhar in 1943. and the formula by Hénon. And in his abstract, Michel sums up the solution, his solution of the problem by saying that dynamical friction does not increase linearly like the Chandrasekhar formula, but it increases slightly faster because there is this log V3 time there. So in the end, what he did show is this, that dynamical friction is a transitory force, that it depends on the perturber's path. Let us remember here he just considered a uniformly constant rectilinear motion. We'll see later that this may change if we have other types of motion. He showed that the logarithmic divergence is an artifact of the unphysical treatment of the problem by assuming that all stars in the system will perturb equally the test star, whether they are close or far away. He showed that the faraway stars behave differently. Then, of course, he needed to find a way to connect with Chandrasekhar's formula, and he does that in the following way. He would try to follow a test star until its travel distance becomes of the same scale as the gene's length. And then he goes, at that time, the friction force becomes stationary. And we should replace, in the formula that I showed you earlier, the travel distance by the gene's length. Since the gene's length depends on the density of stars, this way he has a way of going back to Chandrasekhar's formula that includes the interstar distance, which itself depends on the density perturbation, the density of the system. An interesting thing about this article is that Michel left it there. He was satisfied that with his explanation that if the distance travels of the order of the gene's length, then we can find more or less, because the coefficients are different, the formula of Chandrasekhar, and stopped there and went on to work on the isocurrent potential, etc., that we heard earlier. These results were rediscovered in 1966 by Prigozhin and Severn in their treatment of collisionless systems, where it is assumed that their evolution is not exactly at equilibrium and they depend on time. A number of papers used also this formula by Michel Hénon, but as far as the application for collisionless systems, the story more or less stopped there. Until more recently, this meaning the 90s, there was a big problem until it was solved in 1999, which is that of dynamical friction in a gaseous medium. Dynamical friction in a gaseous medium was known to behave in a very strange way. If you take a perturber moving at supersonic speeds, people convince themselves that the force is basically the one given by Chandrasekhar, while the force on subsonic perturbers doesn't exist. It's zero. There is no friction. And the reason is this. If you look at the density perturbation for a subsonic perturber in a gaseous medium, you find that the density has front-back symmetry. So what you see in that diagram are the level curves of the density. The perturber is moving in the system, and the curves are symmetrical, and so there is no force exerted on the system. Well, that is a big problem because we have a macroscopic force. And we have to remember that Chandrasekhar's formula depends on the inverse of the square of the velocity. When the velocity becomes smaller and reaches Mach 1, suddenly this force becomes zero. And this sounds like an unphysical behavior. The problem was solved by applying the technique that Michel has introduced. When actually we take a perturber in a medium and move it at from time t equals 0 to a certain time t, then it is true that, I forgot to say, when we move it with the constant velocity on rectilinear motion, it is true that the level curves of the density perturbation are symmetric, but not everywhere, because when the perturber started moving, it sent a wave front. It's sort of a shock inside the medium. That's what you see. That's the circle centered. Yes, that's the circle, the big circle centered here on the initial position of the perturber. And so all these curves that you see around the perturber will not contribute anything, but there is this crescent that remains. And this crescent will cause a force. That's a result obtained by an American astrophysicist called Eva Stryker. And she was able to determine the friction on a subsonic perturber. But she did more than that. She also showed that the friction on supersonic perturbers was given by Michel's formula, that is proportional to the inverse of the square of the velocity, with a log that depends on time, on Vt. I show you on the second figure here the comparison between the dynamical friction in a gaseous medium, that is a collisional medium, and the dynamical friction in a collisionalness system, where where the distribution function was taken as Maxwellian. And so you see that in general, gaseous dynamical friction is stronger in this area for between Mach 1 and Mach 2, but for collisional systems, the friction is stronger in the subsonic regime. Then people started doing variations on the theme. They moved to circular motion, and they recovered Michel's formula for the parallel friction. There are two components of dynamical friction. The one parallel to the motion in uniform circular motion obeys Michel's formula. And the subsonic friction is very close to Ostraker's formula. One of the things that were observed, however, in these types of simulations is that the friction obtained from the analytical formula did not describe precisely the dynamics. It was first observed in 1999 and was called the memory effect. There is a certain memory that the force remembers the initial velocity of the perturber. On this diagram, they show as a function the Mach number as a function of time, and you have here what they call the Chandrasekhar formula, which actually is not. It's Hénon's formula plus Ostraker's formula. And the numerical simulation that diverges, as you see, it diverges in this domain. And the question was, what was that due to? And we can actually show that there is nothing wrong with the analytical dynamical friction formula if we take into account the fact that the perturber is accelerated. Let us remember that one of the things that Michel has found in his 1958 paper is that dynamical friction depends on the path of the perturber. Well, for a linear, rectilinear, constant velocity path, it's just Vt. The cutoff is just Vt. But for a more complex motion, we need to take into account the full orbit. It's to understand the dependence of dynamical friction on the initial velocity. One just imagines that the perturber is carrying a rocket and suddenly stops, but if it suddenly stops, there is behind it a wake that still disturbs it. So we can actually calculate directly the analytical dynamical friction force and show that the behavior observed in the simulations is reproduced fairly well by Michel's framework. This brings me to very near the end of this talk, where we enter the domain of nonlinear dynamical friction. The previous works that I talked about are all linear. We suppose that there are very small perturbations, but more recently, with the aid of numerical simulations, people have begun simulating the friction force on a perturber that moves that creates a nonlinear density perturbation. And for the first time, we sort of move away from Michel's formula, where you can see that inside the logarithm here, the divergence has a somewhat strange power of the velocity. This was observed by modeling a supersonic Plummer sphere moving in gaseous medium that is isothermal. The units that you see here are with respect to the Bondi radius, and the perturber here has a max speed of 1.5. These results are just the beginning of our research into nonlinear dynamical friction, but I would like to quote a number of recent applications of dynamical friction in gaseous media to give you an idea of how that original work of Michel influenced in an indirect mode a large number of fields that use dynamic friction in gaseous media. That was understood only thanks to Michel's approach. There's the orbital decay of common envelope binary stars, the evolution of planet orbits around massive stars, the mass segregation of massive stars in young clusters embedded in dense molecular clouds, the orbital decay of kiloparsec-sized giant clumps in galaxies that have redshifts, and also the hot topic of the accelerated mergers of supermassive black hole binaries on subparsec scales by angular momentum loss due to surrounding gas. So, in a way, Michel's first thesis has influenced all the articles that you see, and in a certain way, I think Michel's paper on dynamical friction should be quoted at the same time when one quotes Chandrasekhar's work on dynamical friction, because Chandrasekhar's work was a work of genius, but it lacked an important ingredient, which was understanding exactly why dynamical friction behaves the way it does. Thank you.
In the paper of Chandrasekhar and the very few papers of this amazing list of papers you've given us, the singularity arises because Chandrasekhar neglected the self-interaction of the wake. If you simply do the linear problem, including the self-interaction, there is no singularity. You get a cutoff, you get shielding, just as in the plasma case, except on the Jeans length. And the curious result, I mean, this is, after all, in the linear case, is the acoustic analog of the Cherenkov problem. And when they shoot charged particles through media, they also cut off arbitrarily or do other things. But if you include the self-interaction of the wake, you get shielding. The curious feature of it is that if the movement of the particle is subsonic, it is accelerated. The drag is negative. If it's supersonic, it's dragged in the usual way with the genes cut off.
I think in the special case that Chandra considered, he showed, if I remember rightly, that those particles that move less fast than the particle itself don't produce anything in dynamical friction. It is only the particles that are moving faster than the test star that produces. And I think this is to some degree analogous to what you're getting in the case of a gaseous medium, that sometimes you get no friction and sometimes you get significant friction.
Questions? No? So thanks again.